Alright, so this is a little addendum to the review, which I changed a little bit for this semester. So this is the number 2 from our review. And so let's do this problem. So we want to use the graph to solve the problem below. So you have this definite integral, and over here you have the graph of f, which is in blue, and then g of x, which is in red here. And we can figure out this definite integral by basically adding up areas. What you want to notice though here is that the area of one of these little blocks, the area of one of these little blocks here, one of these little rectangular or square pieces, is 10 by 10. So the area of one of these things is 100 units squared. Alright, so if we want to find this definite integral, what we can do is we can kind of split it up. Because the integral goes through area and you can pull out constants, we can rewrite this as the integral from 30 to 70 of f of x dx plus the integral from 30 to 70 of 2 times g of x dx. And then we can even go one step further and pull out that 2, so we have the integral from 30 to 70 of f of x dx plus 2 times the integral of 30 to 70 of g of x dx. That's 30 g of x dx. And so what we need to do is we need to find these two integrals. I need to find this integral here, and then I need to find this integral here. And if I can find those two numbers, then I can plug them in, add that one plus 2 times that one, and I'm basically done. So let's take a look at the first one. So the first one is the integral from 30 to 70. So here's 30, and here's 70. And we're doing it for f of x, so we're going from 30 up to 70. So I'm looking for this area right there. And I can find that by breaking it into pieces. So we'll break it into 2 pieces. We have this piece, which is a nice square, and then we have this piece, which is actually half of that square. So what do we have here? So this is basically, we're counting by tens, right? So you have 10, 20, and 10, 20. So this is a 20 by 20. So that's 400. And this is half of 400, so that's 200. Which means if you add these together, you get a total of 600 units squared. And because it falls below the x-axis, this is actually negative 600. And then plus 2 times. And so now let's do it for g of x. So let's just wipe this here. And so for the integral of g of x, again, we're going from 30 to 70. But g of x is the red graph. So dotted lines here and there. Oh, and that's nice because this is a positive value, whereas this is a negative value. So that's 2 times 0. And so that's equal to negative 600 plus 2 times 0, which is negative 600. Right? These areas are exactly the same. So if you wanted to compute this area, you could. It's 10 and 10. So what's that? 20 times 10, 10, 30. So 20 times 30, which is 600, divided by 2, which is a 300. And then this is also 300, 20 times 30 divided by 2. But it's actually a negative because it falls below the x-axis. So these two quote-quote areas cancel out. And so my answer is negative 600 for this problem. So let's take a look at the last problem on your review, which is number 6 down here, which is where? Oh, here it is. So number 6. So again, this wasn't on the first video, but it's right here, this little addendum. And we want to determine some things about this function that we have here. We want to determine where the function is increasing, decreasing, concave up, concave down. And I'm going to find any local maximums and minimums, inflection points, and then finally sketch the graph. So here's our new function, and this is a very interesting function because you make it by using the integral, and so we want to use basically the second fundamental theorem of calculus to work with this. Now, as I'm kind of working with this, in the background, if you want, I can kind of have the graph going, but I guess I have to kind of know where to look. So in order to figure out where to look, I should probably do my steps. Right? So let's go through the steps again. Right, so in order to find increasing and decreasing, concave up, concave down, local maxes and mins, we can do these steps. There's 4 steps. The first step is we want to find the critical points. Right, the critical points, and in this case, the critical points of capital F. So that's when f prime of x is equal to 0 or undefined. And so to find the derivative, f prime of x, we use the fundamental theorem of calculus part 2, which says the derivative of this is just this integrand when you plug in x. So you have x over x squared plus 1. This is defined everywhere, right? And you can see that because if you take x squared plus 1 and set it equal to 0, you get x squared equal to negative 1. And of course, the square root, right, plus or minus the square root of negative 1, is not a real number. It's a complex number, so this has no real solution. So what we can do is we can conclude, right, so this implies it's defined everywhere. At the same time, now we can set this equal to 0. So I'll draw a line there, and we'll set it equal to 0. So x squared plus 1 equal to 0. When you multiply both sides by the denominator, so x squared plus 1, it simply goes away, and you just get x equal to 0. So on my calculator, I already know where the critical points are, so I could probably plot this. So if you have your calculator, take it out, and we'll graph this thing. So we'll hit y equals, and in order to graph it, we'll hit second math, and pull up, oops, not the second math, but just math, and go down to number 9, which is FNINT, so hit number 9, and then we can fill this in. So mine's easy because it shows it, so it's just 0 to x, and then hit over, and then I'll put x divided by, and then left parenthesis x raised to the 2 plus 1, so x squared plus 1. And then in parentheses, and then of course I have to say what I'm taking the derivative with respect to, and that's with respect to x. And then I'm going to make my window, and I'll make my window go from -1 to +1 because I found a critical point at 0. And then I'll hit zoom, and then hit 0 for zoom fit, and I'm going to let this run. It's going to take a while for it to kind of run, so I'm going to come back to it because it's got to kind of calculate. Oh, it doesn't take too long. So you can kind of see the graph coming here. So it goes down, and then it comes back up. It looks like there may be some inflection points here too, actually, but we'll see this in a little bit, what's happening. Okay, so let's go down to step 2 now. All right, so at least I have that graph going so I can see things. So I need to do a sign diagram. It's obviously decreasing and then increasing. I can see that from the graph. That's why I say obvious. It's obviously decreasing and increasing. But we'll do it by hand to make sure that is the case, so we can check it by hand. So we'll do a sign diagram. And we have only one critical point, which is 0. And this is a sign diagram for capital F prime. And we're testing for F. And if you put in f prime of -1, and then we'll do f prime of +1. And so here's f prime, and so we'll do -1 divided by -1 quantity squared plus 1. So on the bottom you have 2, on the top you have -1, so this is negative. That tells me the function, yes, is decreasing to the left of 0. Then f of 1 is 1 over 1 squared plus 1, which is a half, which is positive. And so it tells me it's increasing here. And so it looks like we'll have a minimum right there. So what I can conclude here is that f is increasing on 0 to infinity. It's decreasing from negative infinity to 0. And then I have a local min at capital F. Well, this is capital F. Keep writing lowercase f, but capital F of 0, which equals, and so I can come back up here and plug into my original function, and so that's equal to the integral from 0 to 0 of t squared over t, not t squared, but t. Right, so integral from 0 to 0 of t divided by t squared plus 1. Of course, that's equal to 0 dt. So that's equal to 0. And so that's where it's increasing, decreasing, and I have a local min. Of course, you don't have a local max, so if you want to write none for local max, you can, or you can just skip it. All right. Let's go on to the next piece, which is step 3. So step 3 is now we want to find the critical points for f prime. So find critical points of capital F prime. So that's when f double prime of x is equal to 0 or undefined. So f double prime of x equals, well, to find f double prime of x, we have to go back up and look at f prime of x. So this is f prime of x, and it's going to be a quotient rule. So we're going to have a quotient rule here. You have a high function and a low function. And so it's low, which is x squared plus 1, d high, which is just times 1, minus the high, then times d low, so 2x, all over the low squared. So x squared plus 1, quantity squared. And so that's equal to x squared plus 1 minus 2x squared, all divided by x squared plus 1 quantity squared. And that's equal to, then on top you have 1 minus an x squared, because you have plus x squared minus 2x squared, all divided by x squared plus 1. So there's a second derivative. If you, oh, and the bottom's still squared. If you set the bottom equal to 0, you'll see there's no real solution. So basically there's no real solution if you try to solve this, or you can look at it and say a positive plus a positive will never be 0. So there's no real solution, which implies it's defined everywhere. And then when you set this equal to 0, so let's set this equal to 0, 1 minus x squared divided by x squared plus 1 quantity squared equal to 0. We multiply by the denominator to clear denominators, and it goes away on both sides because 0 times anything is 0. And so this implies that 1 minus x squared must be equal to 0. And then we add x squared to both sides. So we get 1 equal x squared. Take the square root, so x is equal to plus or minus the square root of 1, which equals plus or minus 1. So those are my two critical points for f prime. And then finally, we have to do step 4. Which is a sign diagram for f double prime. Right? This one up here was a sign diagram for f prime. And so when we do it, we draw the line. We have -1 and +1 for our two critical points for f double prime, for f prime. And then we're doing an analysis then for f. So here we'll choose a little point f double prime of -2, f double prime of 0, and then f double prime of +2. So just choose a point to the left, in between, and to the right. And we're plugging it into it right here, so what we get is 1 minus -2 quantity squared over -2 quantity squared plus 1 quantity squared. So it's positive on the bottom and negative on the top, so this must be negative. And then when you plug in 0, you get basically 1 over 1, which is positive. And then when you plug in 2, you get the same thing basically you have up here. So you have 1 minus 2 quantity squared over 2 squared plus 1, which is a negative. That's all squared. That's a negative on top, a positive on bottom, so it's negative. So this tells me it's concave up, concave down, and concave up. And that means these are, oops, I got them backwards. Right, so let's undo that. For some reason I put them backwards, right? Negative means concave down. So concave down, concave up, and concave down. Now it's better. And you can see that from the graph, right? So the graph here, it's definitely concave up. And like I said, it does look like it's changing concavity right here. In order to see that, I'm going to make my window a little bit bigger, which I'll do in a minute. But I'm going to do my analysis, right? So make my conclusions from my analysis. So now I know what? I know that F is concave up from -1 to 1, concave down from negative infinity to -1, union 1 to infinity. And then it has inflection points, and I'm going to have to approximate these things. So inflection points where? Well, one at -1, comma, capital, and this is capital F. I keep writing lowercase f, so capital F. So capital F of -1, which equals -1, comma, and I'm going to write this down, although when I do it, I'm going to use my calculator. So 0 to -1 of t over t squared plus 1 dt, which really equals -1, comma, and you can use your calculator and a trace button if you have a graph. So I just hit trace and -1, and it'll spit out my answer. So about 0.347. So let's just say about 0.35. So we'll approximate this, and we'll make it 0.35, and then we'll do 1. So let's do it like this. We'll make it approximately. We'll even do wavy lines just to say, hey, that's approximately. Then we have 1 and f of 1, which again is +1. Oops. So it's +1, the integral from 0 to 1 of t over t squared plus 1 dt, which is approximately, input's 1, and then the output is basically the same. Let's check it just for fun. So you hit trace, you hit 1, you hit enter, and you get out the same sort of answer, about 0.35. So here we'll put 0.35 in parentheses. All right, so that's where it's concave up, concave down, and it gives me an approximation for the inflection points. And then what I need to do is I need to graph this. So in order to graph it, I'm going to need both sets of information here. So let's go up here, and we'll graph it. Let's graph it right here. So I'll draw a y-axis and an x-axis. All right, what do I know? I know that there's a minimum. I know there's a minimum at f of 0, which is 0. So let's put that point on there. Let's do it right here. So this is a minimum. So it's 0, 0. And it's a min. And then I know I have two inflection points. One at -1 and about 0.35. And one over here at +1. 0.35. And again, those are approximations, so that's okay. We'll just assume everybody knows that those are approximations. And then you can see the graph. You might need to make the window a little bit bigger, so let's go from -2 to 2 so we can capture the activity there. And then zoom fit, and you'll see exactly what it's supposed to look like. We'll let it graph, and I'm going to graph it. So here it's decreasing and it's concave up. So basically it comes down like a smile, passes through that minimum, and then goes back up. And then on the right-hand side, it's concave down. So then it goes concave down. So something like that. And over here, it then goes concave down. So something like that. And if we look at the graph, that's pretty much exactly what we have. Right? You can make the window even a little bit bigger. Right? Go to -5 to 5 and resume fit it, you'll see it even looks more like it. But it's a nice way to graph functions, even if they're strange looking functions like this one. Right? You can still use those 4 steps to find where it's increasing, decreasing, where it has local mins, local maxes, concave up, concave down, inflection points, and then you can simply plot the points and connect the dots. And there it is, right? So there it goes graphing. All right, so boom, boom.